Okay, so hello everyone. My name is Satya, and I'm currently a student of the University of Tennessee in Knoxville, which is in the United States. So in somewhat of a contrast to what James talked about, he was talking about an intrinsic flow. So in my talk, the situation is somewhat the opposite. It's an extrinsic flow. So what I want to talk about is like these rotationally symmetric translators of homogeneous curvature flows, which is, as James introduced, these translating translators are something like manifolds that sit inside Euclidean space and move via translation. That's those are the objects we want to talk about. So I was my advisors who helped me with this project are Matthew Langford and Theodora Borney. And a matter of fact, Dr. Langford is actually from Australia, so that's how I learned about this conference and registered to talk. So I want to thank the organizers and like in particular Elena, Grace, and Yossi for giving me an opportunity to talk here. So without further ado, let's get started. So first thing I want to introduce is just a basic review of extrinsic curvatures for those who may not have seen it before. For the experts, my apologies for putting this boring stuff in the beginning, but since we're talking about extrinsic flows, let's start by defining what extrinsic curvature is. So in this setting, we'll be thinking about Mn, a manifold of dimension n sitting inside Rn plus 1. So it's a hypersurface. And let's say it has a unit normal field, which I label n. I mean, it's you can do with just local normal fields, but we'll just assume that it has a normal field n. And so at each point, what you have is you have a map from an endomorphism from the tangent space into itself called the Weingarten map, which what you do is like you differentiate the normal vector in a direction b, and then take the tangential component of it. So that's the Weingarten endomorphism. And so the way we define the curvature is in terms of this. So without too we know that this map L is actually a self-adjoint map, and so by the spectral theorem we know that it has is an orthonormal basis of eigenvectors, and so the eigenvalues corresponding to it are called the principal curvatures. Okay. So we label them kappa I, so I runs from 1 up to n. Okay, so just a word about my presentation style. Like I'll be writing part of it, but things that I can run through, I'll just have like pre-made slides that I'll just run through. Okay, so here's like a few things that you can do with the principal curvatures. So if you have all the principal curvatures, then you can define what's called a mean curvature, which is just the sum of all the principal curvatures, a very commonly studied curvature. Excuse me, sorry. Similarly, we have, if you take the product of all the principal curvatures, that's called the Gauss curvature, which is also so in dimension 2, this is like it's an intrinsic property of a manifold. And so, I mean, besides these, you can also define several scalar quantities defined on the principal curvatures, which we'll be talking about. And we wanna mainly look at what commonly used functions f I can apply my results to. So the focus will be on these functions f. Okay, so let's define what a curvature flow is. So loosely speaking, a curvature flow is something where each point on the manifold. So this is actually sitting inside Rn plus 1, and the velocity is given by a speed function f. Okay, and it's the manifold is assumed to move in the normal direction. Okay, so now precise statement of it. Excuse me. Sorry. Now a precise statement of it. So it's a one parameter family of well, for simplicity, we'll say embeddings. So X is mapped from an n-dimensional manifold across some time interval into Rn plus 1. And so it satisfies the equation that the time derivative of this map, which is the derivative with respect to the second component, right, equals minus f times n. Okay, so f is a so what makes it a curvature flow is that f is a function of the principal curvatures. Okay, so I'll give you a few examples here. So the first example is what's called a curve shortening flow. Okay, so this is in one dimension. So you simply have a curve, and each point is moving at the speed kappa inwards. Okay, so the differential equation it obeys is dx dt equals just minus kappa times n. Okay, so f is just equal to kappa. In higher dimensions, we have flows based on the curvature functions we talked about before. So if I use the mean curvature here, h, right? So this is called the mean curvature flow. Let me just write it down, mean curvature flow. And it's the first example. The second one is I can put, instead of h, I can put capital K, which is the Gauss curvature. So people have studied these two types of flows quite extensively. So maybe I'll give an example of like a flow, like what explicitly one looks like. Okay, so the example I want to talk about is the shrinking circle. So what we do here is, so we take a circle of radius some r naught. Okay, and so we define the flow explicitly like this. It's a map from S1 times a time interval into the plane, and this is given by x of theta comma t, theta being the coordinates on S1. Okay, so what we would want to do is, like, we would want each point here to move with the velocity minus 1 over the radius times the normal direction, and that's what we would want it to do. And in fact, if you differentiate this with respect to time, you indeed see that we differentiate this part with respect to the square root thing with respect to time. That's exactly what you see. So this is, we know that this is just a normal vector, right? For a circle, or in fact any for spheres, like the position vector is the normal. So and here we see the -1 over the radius as the speed with which the curve moves, right? So this is what geometric flows, curvature flows actually look like. Okay, so it's just deforming objects in the normal direction based on some prescribed velocity. So now more to the subject of my talk, like what a homogeneous curvature flow is. So I have to define what a homogeneous function is. Okay, so homogeneous means so this is some function that takes in n variables and spits out a number. Is called alpha homogeneous if if there exists a a real number alpha such that for any z in Rn and any real number or scalar lambda, we have the following holds. So f of lambda times z is just lambda to the alpha times f of z. So the function scales like lambda to the alpha in each direction z. Okay, so examples of it, the mean curvature we talked about. So this is just the sum of principal curvatures, right? So this is 1-Homogeneous. The Gauss curvature, which is the product of the principal curvatures, is n-Homogeneous. Other examples that I've studied in my work are the harmonic mean. So this looks like the summation of, excuse me. So you take the sum of reciprocals of the principal curvatures and then reciprocate it. So this is 1-Homogeneous. Also, the scalar curvature, which is the square root of the sum of products of distinct principal curvatures of distinct indices, I not equal to j. So these are also 1-Homogeneous.
Sorry, Sathya, just quick question.
Yes.
So for the harmonic mean, I guess you're not summing over any kappa-i's that equals 0, right? Ignoring zero curvatures.
For such objects, I suppose it would be undefined at those points.
Okay, right. Okay, cool. Thanks.
Yeah, thanks for the question. And like if at any point anyone would like to interrupt and ask a question, you're more than welcome to. Okay, so this is what a homogeneous curvature flow is. So now I'll talk about translating solutions, which is because I'm studying about translators. Let me define what those are. Okay, so you remember we had a map x from the manifold across a time interval into Rn plus 1. So let's refer to the image manifolds at each time script m sub t. Let's define them as x of the entire manifold at time t. Okay, so we say that this a solution of a curvature flow is a translator if what you see in this image kind of holds. Like if excuse me. So if you have the property that there exists some vector v such that say if such that your image manifold at time t is just the initial manifold M0, which is the image at time 0 plus just t times v, right? If this condition holds, like, so we're thinking of the two sides as sets. Okay, so if this property holds, then we call these translating solutions. Of course, each point need not move in the direction b, right? But as sets, they should translate in the direction b. Okay, so then we call X translating solution. Excuse me, translating solution, and the initial manifold M naught, right? We call it translator. Okay, so so since geometric flows, at least like the ones that I'm studying are invariant under isometries of space and respect rescaling very nicely. The following assumption doesn't lose any generality. So usually we let V just to be the nth basis vector of Rn plus 1. So this is just the vector 0 in the first n coordinates and 1 in the last coordinate. So this is in Rn plus 1. Okay. Let me see. Okay. So I'll give you an example of a translator. So this is in dimension 1. So let me write the parameterization of this object first. So this is, so think of X as a map from, so R is the parameter space, and also so it exists for all time. And so you're mapping into the plane. Okay, so X of X comma T is given by, so the first coordinate is just X. The second one is T plus log secant of X. Okay, so this is something that that asymptotes towards the vertical lines X equals pi over 2 and X equals minus pi over 2, and it turns out that this object moves by translation with velocity equal to just the unit vector in the y direction. Okay, so this is this guy is called the is given this this ghastly name called the Grim Reaper, which is like there's actually a reason for it, which is that if I put any compact solution here and let this flow run, eventually this solution is going to eat up that compact solution because of something known as the avoidance principle in geometric flows. Okay, so this is in one dimension. We want to see what the situation is in higher dimension. So this is, and of course, this is for the curve shortening flow. If I change F, then this object is no longer going to be a translating solution. So for each F, you have a different translator. Okay, so so the reason why I want to study translators is because these are actually examples of what are called ancient solutions. That is, they are defined on a time interval of the form minus infinity comma t. So they have always existed for all previous times. Okay, so these exactly are the objects which you find by rescaling at singularities. Okay, so these arise as okay, so these ancient solutions are really important. In fact, so as an aside, when Perelman was studying the Poincare conjecture, he actually was interested in what are the ancient solutions of Ricci flow. So this is related to what James was talking about. So so this is actually the reason why we want to study translators, because they are important, nice symmetrical examples of these ancient solutions. Okay, so the translators I'm interested in what are called bowl solitons. So which are, loosely speaking, they look like a bowl. Okay, so they have this flat bottom part, and so the reason why I'm saying this particularly is people have found examples of both like translating solutions which kind of look like they have like disconnected portions. Sorry, not disconnected, but imagine rotating this shape around, and so you get and it's known that there are solutions like this which just translate upwards. These are not the objects I'm interested in. I'm more interested in these bowl-shaped solutions. This I'm not so much interested in. So the interesting questions here are, like for which functions f do these exist? Or if they exist, are they unique? And another really interesting question is, when are they defined on all of Rn? That is, they just extend outwards for over like all of Rn, and when do they only exist on some finite, like bounded domain? Right. So these are interesting questions that that I want to answer. Okay, so here are some known results in this topic. So as I said before, the mean curvature flow has been studied quite a bit, right? So there's a result by Altschuler and Wu, which uses elliptic PDE theory to show existence and uniqueness of translators in the mean curvature flow case. Later, Clutterbuck, Schnorrer, and Schulze actually did the same thing, but they approached it using ODEs, still for mean curvature flow. But since they took the point of view of ODEs, they were actually able to calculate the asymptotics of the translating solution as well. So loosely speaking, they were able to prove that these translating solutions are asymptotic to paraboloids. At least, excuse me, they are asymptotic to paraboloids is what they were able to prove. So to be technically correct, I suppose I should say, as x approaches infinity. And for flows by powers of Gauss curvature, John Urbis did some work on this and classified alphas for which solutions are. So he actually showed for what powers of alpha you have this case and which powers of alpha you have this case. Okay, so so that's the known work, and also in some of the examples that I gave previously, we know that the scalar curvature flow by scalar curvature actually yields a solution like this, and the flow by harmonic mean curvature, gives a solution of a bounded domain which sort of is asymptotic to a cylinder. So we want to also know when exactly these things happen. And what I was able to do was not like exactly classify them, but rather give sufficient conditions for when it's the case on the left-hand side, when it's the case of the right-hand side. So these are some known results, and so I'm expanding this work a little bit by expanding the class of functions I study. So they are still like homogeneous functions. Okay, so they are alpha homogeneous for some positive alpha. Positive alphas are particularly well behaved, so those are the ones I studied. For some technical reasons, I also assume that the function f is actually the derivative of it with respect to each of the principal curvatures is positive. But usually people just assume that the function is increasing in each of the variables, but I actually do this. I'll show you in a moment why I have this assumption. And also, I want the function to be invariant under any permutation of its inputs. Such a thing is called a symmetric function. Okay, so the reason why we make this assumption is because, so if B is satisfied, then what I can do is if I have the equation f of x comma, so I have, let's say, y like in all these slots equals z. So let's say this is an equation I want to solve for x. So this can be solved for x. Okay, this is due to the implicit function theorem, right? Because each of the derivative with respect to each of the slots is positive, I can solve for the first slot. Say I can solve for any slot, but so when more precisely, what this means is there exists a function g such that f of g of yz comma y in all these slots equals z. Okay, so this solvability of the first slot is essential because later on I'll be using it to derive the ODE that I'm after. Okay, so let me now state the result that I found. Okay, so this is actually the result of Dr. Langford, Dr. Bourney, and myself. So suppose f satisfies all those conditions I mentioned. The three conditions I mentioned, then there exists a unique rotationally symmetric translator with velocity en plus 1. Okay, for the flow by by speed f. Okay. Moreover, so I have these two conditions that are sufficient conditions for when you have entire like solutions defined on all of Rn as opposed to solutions on a bounded domain. Okay, so if it happens that if the function f, like if my first principal curvature is 0 and all the subsequent principal curvatures are 1, and if f evaluates to something positive, then the asymptotics of my bowl solution is actually analogous to the result of Clutterbuck, Schnorrer, and Schulze. This is actually this is asymptotic to absolute value of x to the alpha plus 1. So in the mean curvature case, alpha equals 1, so this is a paraboloid, plus a little o of x of alpha plus 1. Okay. X approaches infinity. In particular, this function is defined on all of Rn. Okay, so on the second condition, so this is a bit more restrictive. So this holds for alphas bigger than 1/2, and let's say this quantity f of 0, comma 1 is equal to 0. And it happens that remember the function g we defined a moment ago, which is you're solving for x, right? So if it happens that if your print y is infinity and z is 1, and and then the solution to it is for x is like a is positive, then the solution is defined on a ball. And it's asymptotic to the cylinder, which is the boundary of the ball, times, let's say the ball is B, and so your translator is like this, and it asymptotes to the cylinder bounding it. Okay. How much time do I have?
Another 10 minutes would be fine.
Okay. Okay. So any questions so far?
Yeah, just a quick one. So what do you have examples of functions f that satisfy a, b, and c, like common examples?
Yeah, sure. Like for instance, like the second norm of the second fundamental form, the harmonic mean curvature, even the scalar curvature.
All right, cool, thanks.
Okay, so yeah, actually B is kind of a technicality. You can avoid it as long as you can invert the function, make sure that the inverse function doesn't have like infinite derivative. Like, okay, so at least let me show you how, like, what the ODE is, and maybe some of the problems that we run into while deriving the ODE. So first, I'll talk about like how do you get what's called the translator equation. That is the equation that the surface has to satisfy in order to be a translator. Okay, so let's say your surface is this blue object, and its actual velocity is given by the green arrow. Okay, but as a set, it's supposed to translate in the en+1 direction. So what has to happen is, so these two things have to differ by a tangential velocity. Okay, so if that happens, then as a set, this object seems to just move in the en+1 direction. Okay, so so what happens is we have that en+1 plus fn. En+1 minus fn is tangential. So this means that if you take inner product with n, you get 0, right? So which means you get n inner product T n plus 1 equals minus f. Okay, so this is actually excuse me. So this is usually an elliptic PD second order. Elliptic because on the right hand side you have f is a function of curvatures which are second derivatives, right? And on the other side, the normal is also second derivative. So this is actually an elliptic PD in most cases. But if you impose some more symmetries on this object on this equation, it actually turns into an ODE. So, so I'll just discuss a little bit of like what rotationally symmetric graphs look like. So we'll just recall some calculus. So if U is any C2 function, we actually have explicit formulas for the principal curvatures. So the first principal curvature, which of this rotational object, is actually the curvature of the profile curve, right? So this is a formula you've seen in Calculus 1. And then, so the other principal curvatures are given by the formula. This is actually the distance of each of these points in the normal direction to the y-axis. Right, so these are the principal curvatures, and also, so we want to apply this to the translator equation. So we also want to know what n is. So n has this explicit formula. And which is just a 90-degree rotation of the tangent, and that's how we derive this. So if you actually put these together in the translator equation, what you get is that f of the curvatures, which is so first one is u double prime over 1 plus u prime squared to the 3/2, comma, we'll just do n equals 2. The second one is u prime over r times 1 plus u prime squared to the half equals 1 over square root 1 plus u prime squared. Okay, and so just do n equals 2. Also, we'll simplify for our purposes. We'll just say alpha equals 1, so that we can see what concretely the equation looks like, and then maybe I'll just say a few words about how I solve this problem. Okay, so then, but like if you assume that this function is 1-homogeneous and solve for the first slot, it turns out that, so let me say what I'm doing. So you use the 1-homogeneity and you solve for the first slot. And then you get an equation, u double prime equals 1 plus u prime squared times this function g, which solves for the first slot. You'd get an equation like this. So this is so all the theorems that I stated are actually based on solutions of this ODE. So in fact, you can do a little more, because sorry, this is supposed to be u prime. I haven't introduced v yet. So you put v equals u prime, because that's the lowest order derivative that shows up. You can actually turn it into a first order ODE. So v prime equals 1 plus v squared g of v of r comma 1. Okay, so by solving this ODE and studying the asymptotics of this guy, you can actually infer all the things that I stated in the theorem. So how much time do I have?
Getting close to the end, but how much more content do you have?
I'll just like maybe talk about like for the technicalities I face, like just for 5 minutes. Say, would that be okay?
Yeah, if you can wrap it up within 5 minutes, that would be good.
Absolutely, yes. I'll keep it very brief. Okay, so okay, so we just want to study this ODE. So we also, the initial condition I want, since I want the object to be of a bowl shape, I want u prime of 0 to be 0, which is just v of 0 is 0. Okay, so this is the initial condition I have. But note that this equation doesn't hold when I plug in v equals 0, r equals 0. So this equation has at least a coordinate singularity at the origin, right? So that's one of the problems you have. So just to sketch the process, you have to first deal with the origin. So you must show that the solution exists on some small interval containing the origin. Okay, so that would be your first step. And this was by far the hardest part of the proof for me because of that coordinate singularity that we have. The second part is kind of easy. So once you have the solution started at here and like go on for a little bit, then there's a lot of standard ODE results that give you extensibility of solutions. Okay, so then show that the solution can be extended to, let's say, 0 infinity in the first condition that I stated, or that it blows up in finite r in case 2. Okay, and then so once you have these two, then you can start for the asymptotics. You just have to decide, like, figure out what's happening to this term. Like, does G converge to 0 or what? Like, if it doesn't converge to 0, then this function grows like tan inverse, and so it blows up. But if G does converge to 0, then you have a hope that V is actually extensible for all R, right? So this is how you show whether the solution exists for all R, or if it only exists for a finite R. And yeah, like this step was like particularly challenging. So just a word on it as to how you would want to solve it. So if a problem like that happens, then you have to set like part 2 is actually follows from standard ODE theory, like things like the Picard-Lindelof theorem and some basic extensibility results. Like, as long as your gradient doesn't equal infinity, you can always extend the solution by a little bit. Okay, so what you do is, like, you take a sequence of initial value problems and just make the initial condition converge to the origin. Okay, and then see what happens to each of these solutions. Like, so I have a first initial condition and then a solution coming out of it, second initial condition and a solution coming out of it, and then so you get a sequence of solutions. And then what you have to manage to show is that these actually converge uniformly, and then that'll, by CK convergence, you actually, it's a direct consequence that the limit also satisfies the same ODE that you started with, and so you have a solution. So as far as like the shortcomings of this approach, so by this method, I was able to show that, so it's the solution, it turns out, is smooth away from the origin. That part's easy. But at the origin, I was able to show like easily that it's C2. And then for any higher derivatives, you need ad hoc approaches. You need to actually calculate what those derivatives are and show that the derivative is continuous up to that order. In the standard approach, what people do is like they solve like a Dirichlet problem near the origin, and so they use things like the Krylov-Safonov inequality and like Schauder theory to get these things. But the reason why I didn't use them was because if you're using those tools, you have to assume that F is concave and whatnot. Okay, so I didn't want that restriction, so I stuck to the ODE approach. I guess I'll end the talk there. Any questions?
Thanks, Sathya. Let's thank the speaker first. Are there any questions?
I have a question.
Mm-hmm.
I was just wondering if you have plans to like, what are you sort of planning to do next? Are you going to use this result to try and generalize it, or are you going to kind of step into a more difficult problem, or what's kind of the next steps now that you've done this?
So like one of the things my advisor has asked me to do is like, so I focused on the rotationally symmetric example. So I want to see if at least on just bounded domains, like if the domain doesn't have rotational symmetry, can I still prove that translators exist? That's something I want to work on. And so like for that part, I suppose I'll have to use elliptic PDE theory, like actually work out the Krylov-Safonov estimates and so on. So that's something I intend to, that's a possible future direction.
And you won't be able to use this ODE technique in that setting?
Maybe I'll be able to use them like upper and lower barriers.
Okay.
That would be the best I can do with this.
Okay, interesting. Thank you.
Thank you. Yeah, sorry for the hurry at the end, but I hope those things made sense. Yeah.
I thought it made sense. I think it's good.
Thank you. And yeah, thanks to everyone for listening. I appreciate it very much.
Are there any other questions before we thank the speaker again?
I have a question, but it's maybe more of a question for the discussion afterward.
Yeah.
Perhaps perhaps I'll leave it for then if you're going to stick around.
Absolutely, yeah.
Cool.
In that case, let's thank the speaker again. Okay, I'll stop the recording